Alright, silly people, here's the situation. We're going to be calculating the integral of the function x to the fourth minus 2x plus 1 on the interval of 0 to 2, except we're going to be using the Simpson's rule equation for that, um, and then comparing it to the same sort of integrals for the trapezoidal rule. So what I have in this cell right now is actually again, it's the example code for the trapezoidal rule that Mark Newman gives us. Um, and I'm just going to modify it to do the Simpson's rule instead. Um, so just keeping n equal to 10, and then all of these lines actually stay the same. It's actually the first line that's going to be our first change, because the formula to do this is this is given right before the problem statement pretty much. It's h over 3 times f of a plus f of b. So let's start out, before we do any loops, just doing s equals f of a plus f of b, right? Then we have our first loop. 4 times the sum of k from 1 to n over 2 of f of a plus 2k minus 1 times h. That should be fairly easy to do. So yeah, I'm just going to use the remnants of this loop here, and instead of running from 1 to n, it's running from 1 to n over 2, and it's going to be plus 1, so it actually includes k equals n over 2. And then instead of adding f of a plus k times h, we're going to add 4 times f of a plus 2k minus 1 times h. I think that's good there. It's giving me red arrow lines, but I don't think those are real. Oh yeah, they are, because this needs to be multiplied. Now it's good. And then the next loop is 4k in range. It's going to go from 1 to n over 2 minus 1. And I just realized that you should definitely try to put the n over 2 stuff inside the integer function just to make sure that they end up being integers, because Python can be weird like that. It will turn it into floats. So now it's integer n over 2, integer n over 2. It's n over 2 minus 1 in the formula, but so it has n over 2 inclusive. I'm just going to run it from 1 to n over 2. And then inside that loop, you add on to the sum 2 times f of a plus 2 times k times h. And then after both of the loops, you just multiply the whole thing by h over 3, so I'm going to do h times s over 3. And it's going to give us a value which is 4.4004, which is quite a bit closer to the correct result of 4.4 than 4.50656, right? It does ask us to calculate the fractional error on our calculation. So I'm just going to make another code cell here real quick. Copy down our calculated value, subtract off the accepted value of 4.4, and then divide the whole thing by the accepted value of 4.4 and run that. So it's a fractional error of 0.000969, right? It's a pretty small fractional error, all things considered, even though we only did 10 slices for Simpson's rule, which is cool. Part C is modify it to use 100 slices instead, and then 1,000, and then note the improvement in the result. So just so I have all the numbers for comparison, I'm going to run this in a for loop as well. So I'm going to do for n in, and I'm just going to create a list that involves 10, 100, and 1,000 sample points to iterate over, and then tab everything else in the code forward so it prints everything for each value of n. Right. So you get, for 10, again, you get this value. For 100, you get 4.4 even more accurately. And then 1,000, it's not so accurate. Crazy amount of accuracy there. That is to be compared to the same amount of slices, but for the trapezoidal rule over the same integral. Notice how immediately the 10 slices one was way better than the first one. The 100 sample Simpson's rule is a lot, like a crazy amount better than the trapezoidal rule integral. And then this value for the Simpson's rule is just out of this world compared to the trapezoidal rule integral. So yeah, Simpson's rule tends to be better for things like this.